Welcome to section 2.2, the graph of a function. Some of this material we've had before, but we just want to do a quick review. So a function cannot contain 2 points with the same x value and different y values. In other words, this is our vertical line test. So a set of points in the xy plane is a graph of a function if and only if every vertical line intersects the graph in at most 1 point. So for every vertical line I draw, I only want to hit my function in one spot. If I hit in 2 spots, it is not a function. So taking a look at example 1, we've drawn in some dashed lines as vertical line. So here I hit in 1 spot. Here I hit in 1 spot. Nowhere do I hit this function in 2 spots. So this is a function. This function is x cubed. Again, if we draw in a vertical line anywhere along here, we only hit our function in 1 spot. So it is a function. Here we've got a parabola on its side, it looks like. Notice if I draw in this vertical line, I hit my function in 2 different locations. So for the x value of 1, there's 2 y values. So even if that only happens in 1 spot, that is not a function. And finally, we've got a circle. Well, anywhere we draw a line, we're going to intersect our circle pretty much in 2 spots. So this is also not a function. And one of the things when we're talking about functions is we have to think about what are the domains of our functions. The domain is going to be influenced by what values can we not allow, or what would cause it not to be a function. In the case of something in the denominator, we can never divide by 0. So I need to look at this and say what value of x would make the denominator equal to 0. So if I were to say x plus 1 equals 0 and solve for x, this is the value that cannot be in the domain. That's excluded. So the domain is going to be the set of all x's such that x is not equal to -1. So that prohibits us from dividing by 0. Next, it wants to know, is the point 1, 1/2 on the graph? Well, the way we find this out is we take the x value of our point and we put it in here. So if I want to see f of 1, does that equal 1/2? So I'm going to put a 1 in for every x. So 1 over 1 plus 1. 1 plus 1 is 2. So yes, the point when x is 1, y is 1/2. So yes, that is the answer to that question. A little different question here. Is x is 2, what is f of x? Or in other words, what is the y value associated with when x is 2? So f of 2 means we're putting a 2 in for every x in this function. So 2 over 2 plus 1, or 2/3. So that's my y value. The point is x value was 2. The y value we calculated was 2/3. So there's my point. Part D asks us if f of x equals 2. So in other words, is the y value equal to 2? What must x be? Well, to do that, I'm going to set the equation equal to 2, because that's what I'm given, and I'm going to solve for x. Okay, first thing I need to do if I'm solving for x, multiply each side of the equation by x plus 1. X plus 1. They cancel on the right, and on the left, that's a 1 there, I've got to distribute the 2 to the x and to the 1. So that gives me 2x plus 2 is equal to x. I want my x's on one side of the equation and my constant on the other. So I'm going to subtract 2 and subtract x. I'm going to have to draw it down here, which gives me x equals -2. So the point associated with this, when y is 2, x is -2. So the point is -2, 2. Because again, we put the x value first. What are the x-intercepts of the graph? Okay. So x-intercepts we get by setting y equal to 0. So 0 is equal to x over x plus 1. Same thing we did as in part D, but this time I'm solving for x again. Multiply both sides by x plus 1. They will cancel over here, so I get x equals. Now I've got to distribute the zeros. 0 times x is 0. 1 times 0 is 0. So I get x equals 0. So that tells me my x-intercept occurs when x is 0 and y is 0. That is my x-intercept, and that is on the point that's on the graph of f. Okay, let's turn this over and see if we can get through the last example. Okay, so in example 3, we're given a function, which is the average cost of manufacturing computers per day. So this is our equation. If I want to determine the average cost of manufacturing 30 computers, that means I'm putting a 30 in for x. So this is C of 30. And when I plug this in the equation, I'm going to have 0.56 times 30 squared minus 34.39 times 30 plus 1212.57 plus 20,000 divided by, not x, by 30, because we're putting 30 in for that. When I plug this in my calculator, I get back that this is going to be $1,351.54. And I'm rounding to 2 decimal places because it's money. If I did the same with, found the average cost for manufacturing 40 computers, again, I'm going to be putting a 40 in my equation for x. So again, plugging the 40 in, and when I plug that in the calculator, I get $1,232.97. And does it make sense that it costs less if you make more of them? Sure, sometimes that happens. It's what's called economy of scale. Okay, so if we were to manufacture 50 computers, let's see what that would cost. And again, that means I'm taking 50 and putting that in my equation for x. I plug this in the calculator and I get $1,293.07. So a little bit more expensive than if I were to make 40 computers in a day. Okay, we want to take a look at the graph of this. Now it's telling us we want to graph this for x values between 0 and 80. So my scale down here, we're just going to go 10, 20, 30, 40, 50, 60, 70, and 80. And I'm going to go up. Let's say if I want to graph all these, let's go by every 3 of these represents 1,000. 1, 2, 3 is 2,000. 1, 2, 3 is 3,000. 1, 2, 3 is 4,000. Okay. So if I were to graph this and put this in my calculator, over here would be average cost, and over here is the number of computers manufactured in a day. Manufactured in a day. And I'm going to put in the points that we know already. So when x is 30, y was 1350. So let's see, that's about right there. When x is 40, this is 1232. When it's 50, it's 1292, so a little bit higher there. And if I were to plug in a few more values here to graph it, when x was 10, y was under 3,000, about right here. 20, this is about there. And this comes back up a little bit. And there. What this looks like, if I were to connect this with a smooth curve, this looks like this. Okay, great. I've got my function. I've labeled it. I've graphed it. Final thing is, which value minimizes the average cost? So I'm looking for the vertex, or the minimum right here. Putting this in the calculator, I get the minimum is at 41 and 1231.70. That means when you manufacture 41 computers, you get an average cost of $1,231.70. That is the minimum average cost.